Welcome everybody. On this blackboard you see a condensed summary of all the basic facts about complex numbers. Beware, there won't be much examples or explicit calculations, but I rather want you to see the structure, the underlying structure of the complex numbers. So let's take a closer look. So our starting point is the definition of the complex number system by Sir William Hamilton in 1835. Complex numbers have been around for a much longer time. About 3 centuries before Hamilton, Cardano used them to solve cubic equations. And he used strange expressions like square roots of negative numbers, which caused him mental suffering, but he still did it and was successful. But it took 3 centuries until a satisfying, non-mystical definition of complex numbers came along. And this was Hamilton's achievement. So, as a set, the complex numbers are nothing but the known Euclidean plane in 2 dimensions, R2. So, the set of all vectors with real entries, 2-dimensional vectors, which I can visualize as little arrows. Now for the notation, the x1 coordinate or the x1 axis is called the real axis, and the x2 axis is called the imaginary axis for reasons that will become clear shortly. The x1 component is called the real part of the complex number, and the x2 or y component is called the imaginary part. Both are real numbers describing this vector. So then Hamilton defined 2 operations on this set of vectors. The first is the well-known vector addition. I add 2 vectors by just adding their components. Geometrically, this is the well-known parallelogram law. If I have a vector z and a vector w, their sum corresponds to the diagonal in the parallelogram that is spanned by these 2 vectors. So this was nothing new. Hamilton's brilliant new idea was to find a product of 2 vectors. So how to multiply 2 vectors? The product of 2 vectors or complex numbers is defined by the first component is AC minus BD, and the second component is here this cross product AD plus BC. Now this seems very strange and unnatural, but it will become clear why Hamilton did it like that. Very important observation is this: if I take vectors with the second component 0 and I add them, I simply have to add the first entries. And if I multiply them, I also simply multiply the first entries, because if you take this rule with these numbers equal to 0, then this is gone and this is gone. So in this sense, the real number system is contained in the complex numbers. So the complex numbers are an extension of the real numbers, because on the real line, on the real axis, I have the same laws as in the real numbers. And very important, this vector here, 1, 0, the vector pointing in the positive real direction with length 1, is the multiplicative neutral element, because if I multiply any vector AB with this, the result will be AB. Please check this to familiarize yourself with this multiplication. And here is the single most important complex number. The vector denoted by I goes back to Euler, which called it imaginary unit, because back then, before Hamilton, this was defined to be the square root of -1. This, of course, does not make much sense, because the square root of -1 does not yet exist. We will later see that in the setting of the complex numbers, this is a perfectly well-defined thing, but you shouldn't start by defining I like that. This is why Euler called it imaginary. You have to imagine that it exists. But this notation stuck till today, so we denote this vector 0, 1, so the vector pointing in the imaginary direction with length 1, by I. And this complex number has the very important property that if I square it, which means multiply it by itself, it becomes -1. We'll see the details shortly. So to sum it up, complex numbers are nothing mystical or imagined. They are simply the set of all real-value two-dimensional vectors with addition and a rather strangely looking multiplication. Now we're going to explore the properties of this set with these two operations. This vector notation is rather clumsy, and there are two better suited forms of complex numbers for actually doing calculations. The first one is the Cartesian or standard form. If I take any complex numbers, which is defined to be this two-dimensional vector, I can split it up in a0 plus 0b. This is obvious because of this definition. And now comes the important step. 0b is nothing but b0 times 0,1. Please check this using this definition. This here is nothing but the imaginary unit I, and we already said that this here, these vectors a0 and b0, can be thought of as just lying on the real axis, being real numbers. So I identify this vector with the real number a, and I identify this vector with the real number b. And then here remains the only real vector, namely I. For those of you who's familiar with linear algebra, a bit more satisfying is to say here we have a times the 1, this vector, plus b times I. So I write this as a linear combination of two vectors. So in this sense, I can identify the complex number with these expressions. A plus b times I, very important, a and b are real numbers. So, and this is very useful to do actual calculations. If we're assuming that the distributive law holds for this multiplication and addition on C, then I can write this expression here as AC plus ADI plus BCI plus BD times I squared. And now the single most important property of I squared is 0,1 times 0,1. If you use this definition, please do that, you get minus 1, 0, which is the negative of this vector 1 in sub C. Okay? So here I have as real part of this product AC minus BD, and as imaginary part AD plus BC, and here we have this I. And now you should realize why Hamilton defined this multiplication the way he did. Okay, this is nothing mysterious, it's just a much better way to define multiplication than to define I should be something like that and then doing calculations with it. Because in this definition there's nothing mystical. There's no such thing that I have to imagine, but I is simply this vector 0, 1 with this property. So one thing is still not clear, namely what might be the geometrical meaning of this multiplication. Addition is simply adding vectors, but is there an interpretation of this multiplication law? For this purpose, we're looking at the polar form of a complex number. So I could describe this blue arrow by giving you two coordinates a and b. This would be the Cartesian form. But I might as well tell you how long this vector is, and I could give you the angle between the real axis and the vector, and then I would also describe where this little arrow ends. And r and the angle phi are called the polar coordinates of this point here, or of the complex number. So this here is the Cartesian form. Then the real part is in this rectangular triangle, the length of the hypotenuse, r times the cosine of this angle. B here is r times the sine of this angle. I can pull the r out, and now comes a very famous and very important identity. Euler proved that if I plug in phi times I in the exponential function, e is the Euler number, 2.71, etc., then this splits up in cosine phi plus I sine phi. I'm not going into any details here, just telling you this is the famous Euler identity. And if I use this then I obtain the polar form of a complex number. This number can be written as r times e to the phi I. R is here by the Pythagorean theorem a squared plus b squared, also denoted as the absolute value of z. And the angle, sometimes called the argument of the number, is simply the arctangent of b over a, because tangent of phi is b divided by a. You have to be careful. Your calculator might give you for this here, for example, 30 degrees. But if your number actually points in this direction, you have to add pi. So this here has to be regarded mod pi. A special case of this here is one of the most beautiful and famous equations or formulas in the whole of math. If I take phi to be pi or 180 degrees, then of course my arrow is going to point in that direction, in the negative real direction. The length will be 1, because here's a 1. And then this here tells me this must be minus 1. Either geometrically or you plug in pi here. Cosine pi is minus 1, sine of pi is 0, so you get e to the pi I is minus 1. Three of the most important numbers of math, e, pi and I, are combined in this beautiful formula. E is irrational, pi is irrational, and I is not even real anymore, but together this yields minus 1. Very, very nice. And now we can understand what the geometrical meaning of complex multiplication is, because if I have two complex numbers, say r times e to the phi I and w is s times e to the theta I multiply them by multiplying their length. So the length of this new arrow is the product of the length of these two arrows. And then I use this well-known property of the real exponential function, which also holds true for the complex exponential functions. Of course, you have to prove all that. E to the u times e to the v is e to the u plus v. So I may add here these exponents. I can pull the I out, and then I see the angle of the product of these two complex numbers is simply the sum of these two angles. So the blue phi plus the orange theta give me the argument of the product. So multiplication is nothing but adding angles and multiplying the absolute values of the arrows. And this, of course, is not at all apparent from this definition here. So for that we really need the polar form. A nice application of this is called de Moivre's formula. If I have a complex number in polar form, it's very easy to build the powers z to the n. That would be very hard if I would use the Cartesian form a plus b times I to the power of n. I had to expand it using the binomial theorem. It will all be a mess. But in polar form, I simply need to take the absolute value to the nth power, and then I have e to the phi I nth power. Using this, I see this is nothing but e to the n phi I, and then I transform it back using Euler's famous identity, and then here I have the real part of this power is r to the n times cosine n phi. The imaginary part is r to the n times psi n phi. You can visualize it like that. If I take z times z, the angle of z gets doubled. If I take z to the third power, the angle gets tripled, and so on, and the length are just multiplied. So this is de Moivre's theorem or formula, which is very useful to build powers of complex numbers. So now for some very useful notation. If I have a complex number a plus bi, then its complex conjugate, z bar, is a minus bi. So geometrically I do nothing but reflect this arrow on the real axis to get the complex conjugate. And these relations are sometimes useful, but I'm not going into any detail here. The most important fact is the connection between the conjugate and the absolute value, square root of a squared plus b squared. If I take the product of z with its complex conjugate, using the third binomial formula, and using the fact that I squared is minus 1, I get that z times z bar is nothing but a squared plus b squared, so nothing but the absolute value squared. And this is a very, very useful equation or formula, especially when you want to prove things with complex numbers. One neat application is that it's very easy to get the inverse of a complex number. This is not so easy if you take this form and ask you what is the inverse of 3 plus 4i, for example. Now using this formula, I divide by z and divide by absolute value of z squared, and then I have this, the multiplicative inverse of any complex numbers not equal to 0 is z bar, the complex conjugate, divided by absolute value of z squared, or here written in Cartesian form, a divided by a squared plus b squared is the real part, and minus b divided by a squared plus b squared is the imaginary part. And with this it's very easy to find the inverse of a complex number. These two are sometimes useful when dealing with complex conjugates. They are additive and multiplicative. The same for the multiplication holds true for the absolute value. This is the same as that. But the absolute value is not additive. There's no equal sign here, which we already know from the real numbers. This is the famous triangle inequality. In the real numbers, this name didn't really make sense because there was no triangle. Now here with the complex numbers, it is obvious why it is called triangle inequality. If I add here two complex numbers, I can visualize it like that. So the sum is simply this vector, and I have a triangle. And then, of course, the length of this side can never be larger than the sum of these lengths of the two other sides. Only in the case when they all point in the same direction, I have equality here. Otherwise, I have this famous triangle inequality. So now we're taking a look at some algebraic properties of the complex numbers. First of all, the complex numbers form a field. The only things that remain to be shown is that the distributive law holds, which is not hard but a bit tedious, and that every element has a multiplicative inverse, but we just did that before using the complex conjugate. The rest is almost trivial. Very important fact is it is not possible to put an order relation on this field. For example, to say I is larger than 2 is not possible. And this was one of the main sources of confusion for the old mathematicians when they were dealing with the complex numbers, because they implicitly assumed that it must be possible to have an order relation. I'm not going to prove that, but you should remember it's not possible to put an order relation on this field. The most important algebraic property is that the complex numbers are algebraically closed, which means that every polynomial with complex coefficients always has a root in C. This is the celebrated fundamental theorem of algebra, and in every proof known today you need at least a little bit of calculus, which annoys the hell out of the algebraists. A simple application is this polynomial z squared plus 1. This is obviously a complex polynomial. Over the real numbers, this wouldn't have any roots because no real number squared can equal minus 1. But in the complex numbers, by the fundamental theorem, roots exist. And here we can explicitly state that the roots are plus and minus I, because plus minus I squared is the same as I squared, and I squared is minus 1. This was the most important property of the imaginary unit. So this polynomial has two roots. Or more general, if I have a second order polynomial ac squared plus bc plus c, a not equal to 0, then this always has roots, and the famous quadratic formula, which is exactly the same as over the real numbers, because in the proof I need nothing but the field axioms. This formula holds with the novelty that now the roots always exist. Remember in school when you calculated here square root of minus 4, you made a lightning symbol and said this is not possible, doesn't exist. But now over the complex numbers, roots always exist. on a side note, this is an existence theorem. It tells you that there is a root. It doesn't tell you how it looks. Actually, for n larger or equal to 5, it's not possible to give such a formula. But here in this case, what is the root? To avoid confusion with a, b, and c here, I call the real and imaginary part d and e. The square root of a complex number is given by this formula, which is not as bad as it looks on first sight. Here is the sign of the imaginary part. That means if the imaginary part is negative, I put a -1 here. If it is 0 or positive, I put a +1 here. So this is simply plus or minus in front of this root. And these two roots are ordinary roots over the real numbers because the entries are non-negative. Here I take the absolute value of this number plus its real part divided by 2. Here I take the absolute value minus the real part divided over 2. This cannot be negative. And this gives me the square root of this complex number, and this clearly always exists. The root of a complex number must lie in the upper half plane. This is guaranteed by this plus sign here, because I always have two possibilities except for 0, but this is a technical detail. This here is very, very nice. If I take the complex number -1, which is -1 plus 0 times I, and use this formula, please check the details yourself, I get I. And in this sense now I can say that the square root of -1 is a well-defined object over the complex numbers, and it is the imaginary unit. So in retrospect, this justifies this here, but still this is a nonsensical definition. Yeah, you cannot define I simply to be something that you don't know yet exists. But in the end, this approach may be justified by using this formula. Okay, if you have a calculator at hand and can calculate the argument, the angle here, then of course it's much easier to compute the complex square root of this number in polar form. It's simply the real root of the length of the arrow, and then you have to divide your angle by 2, because what does complex multiplication do? If I square a number, I simply double its angle. So if I want the square root, I have to take the angle divided by 2. So to conclude our little summary, we take a look at geometry over the complex numbers. I'm not sure if this is good English, but maybe I should have called geometry of complex numbers. For example, if I want to describe a circle in the plane, I identify the plane with the complex numbers, and if the center is capital Z, then all the points on the circle fulfill this condition, namely that the distance between capital Z and capital Z is equal to the radius of the circle. I also can describe, for example, here a perpendicular line through the midpoint of 2 points by this condition, and in general all straight lines and all circles can be described by this complex equation. A and C are real numbers, B is a complex number, and they have to satisfy this condition. If A is 0, then this describes a straight line. If A is not 0, then this describes a circle. But I'm not going into any more detail here. Just to give you a glimpse of how useful complex notation can be to describe elementary geometry. But this so far didn't use the multiplicative structure of the complex numbers. This is simply the length of a vector, so this is already well known. Here, this is very nice. This simple equation, z to the nth power equals 1, the solutions of this equation describe a regular n-gon. Here, for example, a regular pentagon. In general, the solutions are called the roots of unity, denoted by the Greek letter zeta, zeta sub 0 till zeta sub n minus 1, where zeta index k is e to the 2 pi over n. I take 360 degrees divided by n, and then times k, and of course I need my I for the polar form. You can easily check that if you take this here to the power of n, you end up with e to the k 2 pi I, which is a multiple of 2 pi, so you always end up with 1. And to understand the geometry, if I multiply this number, say zeta 1 with itself, the angle gets doubled and I get zeta 2. If I take it to the third power, I get zeta 3 and so on. So this is a very neat way to describe regular n-gons in the real plane using complex numbers. Okay, that's it. Those were, in my opinion, some of the most important and basic facts you should know about complex numbers. If you enjoyed this video, please consider giving it a like or subscribing to my channel. My other videos so far have been in German, but I'm planning on doing the whole unit on complex numbers in English. So hopefully I'll see you soon.